Good morning, good afternoon, or good evening, depending on where you are. Welcome to this session of the AMPL Enterprise webinar series. I am Eduardo Salazar. I am a technical account manager at AMPL Optimization, and I am joined today by Tiancheng Shang from Cardinal Operations, the team behind the Cardinal Optimizer, or shortly known as COPT. The title is From Portfolios to Power Flow. And the reason is that today we will be solving a wide range of problems using COPT and AMPL. We'll be taking one solver and one license across different problem types to showcase the different capabilities of both AMPL and the solver, from a linear problem to a non-convex quadratic problem, as well as some conic optimization. And we're going to do that without rewriting a single model. Everything you are going to see today is an ordinary AMPL model and then some Python code. So first, the agenda, housekeeping first. Three quick things. This session is being recorded. The recording, the slides, and the collab notebook will be sent out to all of the attendees after the webinar is done. We're going to be running about 75 minutes, 60 minutes of content, and then 50 minutes for Q&A. And third, please put questions in the chat as they occur to you. We're collecting them and then we'll be taking them at the end. On the plan, Tiancheng will start with who Cardinal Operations and where COPT is today. Then I will take over for a little bit of the Ample integration, the three demos of the problems we'll be solving today, the COPF problem, an ACOPF, and then a conic optimization portfolio problem. And then lastly, we're coming back together for the integration of Ample and COPT and the licensing, and obviously the Q&A. So without further ado, Tiancheng, over to you.
Okay, thank you, Eduardo. Very glad to be here. I'm Tiancheng from the COP team at Cardinal Operations. A little bit about our company and the product. So Cardinal Operations was founded in 2016 and is currently headquartered in Shanghai and with offices across Asia and Europe. And our work centers at decision and computing intelligence for application areas including supply chain, manufacturing, energy, finance, and among many others. And our solver, Cardinal Optimizer or COPT, was introduced in 2019, and now the most recent patch release is 8.0.5, and it has been growing a lot into now a full capacity, high performance commercial solver with users across different continents and more than 80 countries. And so for today, the key point is that COPT is well integrated into with AMPL, and a modeler can take advantage of the AMPL workflow while selecting COPT as the underlying optimization engine. So let me briefly show how COPT has developed. So the 1.0 version was released in 2019, and it was a very basic simplex LP solver. And on this slide, this timeline shows COPS progress from 2019 to the current 8.0 major version. And over the period, our capability has expanded through the various continuous optimization types, including the barrier LP solver, the second order Korn, conic, and quadratic and quadratically constrained optimization, semi-definite optimization, and their mixed integer variants. And AMPL has integrated COPT since 4.0 in 2022. And so recent addition to COPT, including GPU native PDLP solver and GPU native barrier solver for LP and different continuous optimization problems. And we also invest our R&D effort a lot into the MIP developments. And we also added the non-convex MIQP solver, which will be demoed in one of the demos at Eduardo's notebooks.
Yep.
Can I go to the next slide? Can I go to the next slide?
Yep. Okay.
Yeah.
This one.
Okay, the previous one, sorry.
Okay.
There's
Yeah.
a time lag, yeah. And this slide, I think, pretty much shows the comprehensive capability of COPT. As a commercial solver, we need to, or we have been used in different operating systems, different hardwares, and the enterprise have been using us in a single performance solver or in a local network or in public cloud, in private cloud, or has been get authorized through the web licensing service. So we have offered all these options. And for input format, we have supported the widely used LP MPS and also CBF for Cornic programs and SDPA for semi-definite programs, and also the OSIL format and or OWN bin format. And we are also integrated into many different programming languages and third-party modeling tools, which were listed, partially listed in the left bottom section. And the the right bottom section shows the problem types we can solve uh, at the moment. I think we are also adding the global solver for MLNLP soon. Maybe this year or maybe next year.
Very exciting then.
Mhm. So this map shows our global footprint. We have lots of academic users and commercial users across more than 80 countries, more than 2,000 uh, research institute and universities, and we have more than 30,000 direct users. So by direct users, this does not include the users from AMPL to call COPT in their AMPL codes. And we are also actively engaged in with these academic organizations. Uh, on the bottom, maybe you can see us at the exhibition hall or different sessions in at Inform's usual SMP, iForce, or other conferences in management science and operations research. And here is some of the clients we have served in the past 10 years. So I think we have served more than 500 enterprise users across more than 20 different industries. And I list quite a few from the energy sector and from the finance sector, which is related to our topic today. Can we go to the next? And this is one example which illustrates the value of bringing the modeling power from AMPL and the solver technology from COP together. So this is a commodity trader at EZPADA who has been using AMPL and COP, and they reported a 100 times performance speed up after moving its logic into a streamlined AMPL and COP optimization framework. And this is just one example. I think we have much more than that, but still, it's good to see those numbers. And it's also a real life demonstration from production uh, compared to the open benchmarks that could be overtuned, right, by some solver vendors. Okay. Yeah, and I think this table summarizes the problem types that can be solved with AMPL and COPT. And in the second column, uh, it briefly describes where the difficulty could come from. For example, for LP, it's mainly the scale or the supersparsity or density of the problem. And based on the structure, you may need to choose whether you use simplex or barrier or PDLP or on CPU or on GPU. And yeah, and I think for the non-convex QCQP and NLPs, which will be demoed later, uh, the difficult part is the bilinear terms, which will be solved by spatial branch and bound uh, by COPT. Mhm. Yeah, and as of the current state of COPT 8.0, it was actually released last year before the Informs in Atlanta. And we mainly focused on GPU native acceleration, including some improvements on the PDLP, which was introduced in 7.1 or 7.2, I think, in 2024. So it was further improved. And the GPU barrier was newer, and it was released during the Euro conference in Leeds in the UK in June 2025. And it supports uh, different types of continuous optimization problems, including LP, QP, QCP, and also SOCP and exponential cone problems. And third, we introduced the spatial branch and bound for non-convex QCQPs. Uh, I think in the past we have to solve it locally. We will stop with the local optimum, and now with the spatial branch and bound algorithm, we can solve to global optimality. And I think in the future, maybe the version will be releasing in November or in October this year. We can expect more on MIP performance, especially the uh, maybe faster feasible solutions and also faster convergence on really challenging problems. And also we made some progress on the QP and SOCP progress as well. Um, we also developed some user-friendly features and also some advanced features for enterprise users, including the HTTP-based cluster manager for our cluster license or cluster deployment. And there will also be more on the GPU acceleration. Okay, the GPU story. I think Professor Haihao Lu from MIT, uh, his team wrote a nice summary on the development of PDLP. And from the solver market, solver vendors perspective, uh, all these solvers have been hearing in the past maybe 20, 30, 40 years. They have been relying on the CPU clock rate for performance improvements from the hardware side. And we we really didn't take advantage of the hardware development of machine learning, deep learning, and transformer, uh, which has been pushing the frontier of GPU a lot, and also recently NPU, QPU, and other specialized hardwares. So I think in 2023, our development team and our scientists, together with Professor Lu's team, wrote a paper on CU-PDLP, written by C language. And shortly after that, we released the PDLP in our commercial solver. So CU-PDLP was open source, and uh, COPT is commercial. And then after that, I think QOPT and also other solver vendors followed this trend. They introduced, uh, I think, mostly PDLP. So that was the one methodology to get rid of the complex matrix computation, such as LU decomposition, such as Cholesky decomposition, Cholesky factorization, which were not easy to parallels on GPUs. And we also tried it the hard way. So we also implement a barrier solver on GPU, which we found a way to parallel the Cholesky factorization efficiently enough so that it can show advantage compared to industry grade CPUs. But still, I think we have to be careful when to use GPU and which algorithm to run on GPU. It will be depending on the scale, the sparsity, and some other features of the uh, LP and of the problem. And okay, I'll give the floor back to Eduardo for the demos.
Thank you, Cheng. Yeah, so that's it for the engine itself for the solver. So let me just spend 5 minutes on how to connect with it with Ample. This is the whole integration, and I mean it's a short section because there's not much to say. You set your option solver, COPT, and then you set your COPT options, whichever specific parameters you're tuning for the solver itself. Um, Nothing else changes. Nothing in the mod files, nothing in your driver code using AmplePy or whatever of our APIs. Um, you don't change anything of your variables, your constraints, or your objective. And that's the beauty of Ample, right? The Ample MP driver formulation can also tune specific problem types and constraints for in the best way, the tightest way it can for COPT. And this is what makes it possible, right? To write the model a single time, and then you can drop constraints, you can add constraints, you can switch solvers, you can switch algorithms which you want to run the problem on, and so on. So as you can see, it's quite easy. And today we're going to also follow an interesting modern workflow, which is the Amplify workflow. Typically, for long-standing Ample users, you may be familiar with the model hosted in your .mod file, and then your data and orchestration either in .dat files or in .run files. That still works. However, as we have moved on to a more modern world with more complex problems and also data sources incoming from a wide range of capabilities, from machine learning models to SQL databases and so on, we have decided to recommend for our end users to actually follow a modern workflow with AmplePy, which is our Python API that allows you to work with the same models you used to work before. That doesn't change, but now all of your data, your orchestration, and so on happens in Python. And this allows you to use the whole Python ecosystem, NumPy, Pandas, TensorFlow if you're doing machine learning stuff. And then this has an interesting consequence for deployment because now you can deploy in Google Colab, in Kaggle, a local install, a Docker container on the cloud, and so on. So it's quite limitless. So we'll be following this workflow today. This is how you install Ample and COPT using the Python API. You simply install pip install AmplePy, and then using our installation module, you install the COPT solver. And then for a notebook, you just import AmplePy and these two functions. And with the Ample notebook function, you will construct your, as the name implies, Ample notebook object that will be connecting with the Ample modeling language and the solver itself. And you specify your license, and this should get you working with COPT and Ample. To get your COPT trial and your Ample licenses, be sure to visit our Ample portal, portal.ample.com, and request a commercial evaluation license for COPT. Um, More or less, this is what what we will be working with: the LP method and the ALG GPU mode and non-convex parameters. The first one, the LP method, as the name implies, will select the method for the LP problem. If you set it to 1, it's dual simplex. If you set it to 2, it's barrier. If you set it to 6, it's PDLP. And once you have chosen which method, you can select the GPU mode, which is 0 for no GPU at all, just running on the CPU, 1 for PDLP on GPU, and 2 for barrier on GPU. Non-convex parameter also will set the solver for non-convex QCQPs. As Tianchen said, they have COPT has a local solver, but there's also the spatial branch and bound, which will arrive to the proven global solution, and then we will see that in action. And lastly, the outlet and timing, these are for logging purposes, for seeing information about what's happening with the solver, and we will use those as well. Okay, so now let's get into the fun stuff. Our first demo, what are we actually solving? Demo one is a multi-period DC optimal power flow. So if you work in power systems, you can skip the next 6 seconds, and if not, it's a very basic explanation. We have a transmission network. We have a set of generating units with different marginal costs, and we have demands at each bus that varies over the day. And we want to find the cheapest way to meet that demand while being respective of the constraints, the physical constraints of the network, such as the thermal limits of the line, the output limits of each unit, and the ramp up of each unit, which means how much can they change between hours of their output. Two things make it the first try demo. This is a pure linear problem because we are doing a DC approximation. The real world is not DC, actually, it's AC, but for these purposes, we're just assuming it's DC. We are using the B theta formulation. The formulation is linear, so it says sparse, and the merit order cost is also linear. So PDLP and GPU methods can play and solve these problems. This is not a toy. This is the LP core at the core of market clearing and unit dispatch. So it solves thousands of times a day by system operators. So the version I am running is synthetic, so I can scale it. But this structure is actually the real structure that real end users end up using. This is more or less a little bit of the model in detail. We have our sets of buses, our lines, our generators. We have our time periods. We also have our variables, the generation of each possible generator at each time, the theta variable, which represents the electrical component of it, the flow over each line, and we want to minimize the total cost of our generators, subject to and respecting the flow in the network, the balance in the network, and also the ramp up of our generators and the thermal constraints. Um, if you see, there's nothing specific about COPT. We are not doing any solver hints. We are not doing reformulations or conditional blocks. The same lines will fit the problem, and we will change the algorithm as we go. And the same model you could fit to different solvers. But for today, obviously, we are focusing on COPT. I am not going to find to hand tune this instance. We're just solving it as is, and we will see how COPT performs. Um, okay, so this is the setup. We have the same model file, we have the same data. We are just changing the options of the GPU itself. We are running dual simplex, barrier on CPU and GPU, PDLP on CPU and GPU. And we have this is our data synthetic meshed grids. We have 60 buses over 24 hours, 150 over 24 hours, 400 over 2 days, and lastly, 900 over 48 hours. So this one is over 100,000 variables, still a linear problem, but a larger one. And our hypothesis, before we run the code, is that the Barrett's factorization cost will grow the fastest. So now on running on CPU. So actually, as you start growing the scale, then GPU will pull ahead of CPU. So please let me know if you can see now this part. Tenchen, can you see the Colab presentation?
Yes, yes.
Okay. So I'll be keeping over the code. This is the model itself in more detail. It's around 40 lines of ample code. We have our ramp up, ramp down constraints, the reference angle, which should be set to 0, and yeah, that's it. On the Python code itself, as I was saying, this is what we will be setting up our methods for running on the CPU or the GPU. This function will generate our synthetic data. with a diurnal load profile, some random number generations, the susceptance matrix, the thermal limits, and so on. And lastly, this is the part of the AMPL driver code. So we create an AMPL object, we read our model, and then we start setting in the data within Python of our model. So we could be using pandas data frames, SQL query results, dictionaries, objects in Python, whatever works for the solver itself. And lastly, we just invoke the AMPL solver, sorry, the AMPL language with the COPT solver, and then we retrieve the results and we will find out how well it performs. So if we run this code with our pairs of bosses and periods, this is actually what we get. First, when we run for 60 bosses and 24 periods, we get 4,000 variables. So I'll go back to the presentation, which has the table itself. Dual simplex runs in less than a second. It's tied with barrier and CPU. However, our barrier GPU and PDLP in both CPUs and GPUs are run slower, which makes complete sense. This is a very small problem. However, once we start scaling the size of the problem, we can see that barrier pulls ahead of dual simplex on CPU. But when we get to the 50,000 variable mark, we see now that PDLP GPU is quite fast, across 3 seconds when compared to the dual simplex, which is 17 seconds. And lastly, on our biggest instance size, we see that dual simplex now takes over 3 minutes. Barrier CPU is still competitive with 27 seconds almost. However, Barrier on GPU and PDLP on GPU are the fastest. Barrier on GPU runs in less than 16 seconds, and PDLP on GPU runs in less than 11 seconds. So, as our hypothesis was tested true, Barrier wins in the small and mid cases on the CPU. However, once you have a large scale LP, and even this 100,000 variable LP is not super large, like as you have seen in, well, depends on your context, in academia or industry, we may see LPs of millions of variables. So even at this not so large scale, GPU is already almost 20 times faster than dual simplex and 2.5 times faster than barrier on CPU. And as you saw in the code itself, we didn't change anything of the model. We're just changing the solver itself. And we see these same results I reported. These are what is being shown in the code. 205 seconds, 26 seconds, 15 seconds, and so on. And we see the same objective. However, one thing to keep in mind when running GPU algorithms is also the numerical tolerance of your problem. We may be reaching the same optimal objective value function. However, we also have numerical tolerances to keep an eye out for, especially in the constraint sides. And I will say this is the biggest drawback of GPU algorithms right now, is the tolerance. If you want to converge to really tight tolerances, then the GPU will spend more time fixing the problem and doing the crossover to get to that tolerance. However, if you're running large scale GPUs, which with a moderately acceptable tolerance, then this is the right solver for your problem type. Um, we are now moving to our second demo, which is actually nonlinear. Demo 2 is what happens when you do not linearize the physics. In AC optimal power flow, AC is standing for alternating current. Each bus voltage is a complex number. I am writing it in rectangular coordinates. V equals E plus JF. So when you write the injected power at a bus using the admittance matrix, Y equals G plus JV. Every power flow then turns out that it's now a product of voltage components. So the real and the reactive power balance equations are now bilinear equalities. So now it's a non-convex quadratically constrained quadratic program, non-convex on two separate accounts. You have your equalities, which are bilinear, which is bad enough, and then the lower voltage magnitude limit, which is E squared plus f squared larger than v mean squared. Now this is a complement of a disk. It's not a convex set, and it's actually the outside of one convex set. So this is a canonically hard problem in power systems. There's a very large literature on relaxing it, on convexifying it, and then unbounding it. For the demo purposes, we are working with a tiny instance as for this hard problem as is, just a three bus mesh loop on a system with 100 megavolts amperes of base. We have cheap generation at bus 1, expensive at bus 3, and load at buses 2 and 3. So it's small enough that it can prove global optimality in a fraction of a second, which is what I'm going to show you rather than me describing. Since this is a non-convex problem, we are going to be trying out the two solvers from COPT, which is the local solver, and the global solver, which uses the spatial branch and bound. So I'll be jumping back to the code itself. This is a little bit of the model. It looks similar to the DCOPF model because in the end it's more or less the same problem, but with different physics. You have your set of buses, of generators, the loads, and since we are working with the AC formulation, we have to take into account the real power and the reactive power, the real part and the imaginary part of our admittance matrix, our limits and costs of the generators and the buses, our decision variables, which will now include the real part of the bus voltage and the imaginary part, and obviously the PG and QG of these both components of real and reactive power. We are minimizing the generator cost, same as in DCOPF, but now our power balance should account for the real and the reactive components and the voltage magnitude limits, which this lower bound is actually non-convex as well. And lastly, our reference angle is set up to 0. Um, and this is our Python code. As I said, we have three buses and two generators sitting on bus 1 and bus 3. We have our load in the real and the reactive components and our lines, which is just a three-line loop. With this function, with the build function, we are reading the model from AMPL and setting the data corresponding to our Python code above. We solve and we retrieve the information, the variable functions, and so on. So with this line, we are using the global spatial branch and bound, which will give us the proven optimal solution. And with this line, we're using the local solver, which, as we will see soon, something happens with the local solver. So we set up the solver, we start solving with AMPL and COPT. As we can see, it starts branch and bound, with the spatial branch and bound actually. And obviously it recognizes as a non-convex QCP. And we start seeing that in less than a second, obviously, we close the problem. We reach our optimality gap of 0. And we have our objective function of $20 per hour to set up to run the grid itself. However, something interesting happens when we solve with the local solver. Turns out that starting out from the scratch, the local solver of COPT reaches an invisible local point, and it does. And even if you were to feed it the global solution, it will fail as well. Why? Because we have non-convex powerful equalities, and since it's an extremely hard problem, the local search will get stuck in the local invisible point, which is actually the motivation of why we are using the global solver above now. This is not a failure on COPT, rather it's showing how hard these problems are. And as you saw, this is an extremely small problem, just three bosses. So real world has thousands of bosses. Um, and this shows you both the drawback of local methods and also the overall strength of using a global method, which will get you to the optimal solution with an optimality gap guarantee. Um, I guess this is also how you can see COPT working with nonlinear problems. So we have seen LPs, now NLPs, more specifically non-convex QCQPs, and this is what's important. The real world is nonlinear. We typically tend to linearize it to approximate it to convexify it to make it work in a solver. However, as solver technologies advances, we can now start working directly with these nonlinearities, with this bilinear physics, which arise not only in OPF but also for pooling or blending fields systems. However, this comes at a price. The spatial branch and bound is exponential in the worst case. So you should start small with your nonlinear problem and scale and see how the problem performs in your solver. Lastly, last demo, this is a change of domain. This is not only a power systems story. We are going to be looking at a portfolio optimization model. If you are familiar with the optimization theory of portfolios, it's basically a Markowitz problem. You have your set of assets, you have your set of it's not your set, your covariance matrix, and your expected returns. We are going to be scaling this problem in three different stages, scaling difficulty. The first one is textbook Markowitz problem. We're going to be minimizing variance subject to a floor unexpected return. This is a convex quadratic problem, so this will be solved by Ciott's barrier. Stage two, this is now a second order conic programming or a QCP problem. We are going to be maximizing the expected return subject to a budget on volatility, so it's actually the first one, but the other way around. And the risk constraint is now a convex quadratic constraint, sorry, a second order cone. And stage three will add constraints that basically every practitioner out there actually needs, which is hold or do not hold a binary variable per asset, a cap of at most k names in the portfolio. So now we have cones and integers. So this is now a mixed integer second order conic programming. And COD will solve it with the branch and code solver. And I want to show you that the model itself doesn't change. We are adding and dropping constraints as we go on the fly. Portfolio on one slide. This is what our model actually looks like. We are declaring both objectives at once and all of the constraints, and then we will be working with those as we interact with the Python code. For the stage one, we are dropping the risk cap formulation constraint, the linking constraints, and the cardinality cap. We are restoring the return floor, and we are fixing y. For stage two, we are dropping the return floor, we are restoring the risk cap, and we are switching the active objective to the expected return, which is now a conic problem. And stage three basically restores all of the constraints and then fixes the binaries. And now this is a mixed integer conic problem. You see, we're using drop, restore, fix, unfix, objective, and so on. So this is the whole regime behind the switching of the model. It's worth knowing because it changes how you build these things. We are not maintaining three different models, rather a single one, and we're expressing the variance of the single model with different constraints actives. So hopefully people are familiar with the Markowitz notation. If not, basically sigma is the covariance matrix between our assets. We have the risk theory and the expected return theory, which is quite interesting. And okay, I'm switching back to the code. As I was saying, this is what the model looks like. You have your set of assets, your expected return of each asset, the return covariance matrix, the required return out of these assets, the volatility budget, the max number of holdings, and your objective function, your variables, which let you know which assets are you holding in your portfolio and which ones are for the long-only portfolio weights. Okay, so this is the Python code itself, which I don't know why it looks like this. Well, anyways, we have our small factor model covariance matrix. You have your variances, your covariances, your expected returns. We are building the model with AMPL. We read the model and then we set the data. And this is across three functions. We are building three different models from the same model file. We are dropping the constraints. We are restoring some constraints, and we are fixing some of the variables. For the first one, which is QP, we are doing barrier. For the second one, which is a second order conic programming, we are doing barrier as well, but this is now conic. And for the third one, since it's now a MIS-OCP, it's now a branch and code solver. So we'll see how COPT performs actually. For the first one, the stage one convex QP, COPT reaches this optimal value of 0.12, and we are respecting the return, which is greater than 0.10, obviously. For the stage two, it's now a second order or quadratic constraint problem. It's still convex, but it's now conic. The objective is now 0.005. Why? Because now remember that our objective is not the return itself. Yeah, sorry, it's now the expected return. Our volatility budget of 0.733, 0.0733, and it spends it all basically on the return. The return is now actually further up ahead and concentrates out to 6 names. And lastly, for the stage three, which is the mixed integer second order conic programming or mixed integer conic, um, this is what we get. Before I solved this, I solved a small mixed integer QP to find the minimum achievable volatility with only three names, which comes out to be 0.076, this one. So now when I set the stage three budget plus 15% above that, a three name portfolio actually cannot be diversified as a 10 name one. So if I reduce stage twos, the model will simply be infeasible. So I am anchoring the budget to what's achievable actually to make the comparison meaningful. So now stage three returns 0.1348, volatility of a budget of 0.0874, which holds actually three names, three assets, A4, A5, and A9. So what's the takeaway? If you see, we have the same data, the same model, nothing has changed apart from dropping and adding constraints as we go. Let's go back to the presentation. And this is a recap of the methods we're using in COPT. For the first two, since they are convex, we are using barrier. For the third one, which is now a mixed integer second order program, we are using the branch and code specified for conic programming. And we see that we are getting better returns as we go, obviously, because we are starting to take more constraints into account and we are specific of the names the portfolio starts holding. And this is actually the main takeaway I would like to get. You model once, and then based on your real problem expectations, you start scaling difficulty without restructuring your whole model. And then obviously you have to tune out your solver as well to find out which algorithm works the best for your problem types. Return goes up as we move down the table. However, volatility does as well. SH3 does not dominate SH2. It achieves a high return, however, with a high risk budget, and you hold only three names when compared to holding six names. And the concentration is exactly what this means. For a given risk budget, a three-name portfolio will underperform a six-name, which is the trade-off the cardinality cap actually exists to expose, right? And so, um, lastly, when to reach for COD from AMPL. As you saw from the beginning and Tian Cheng's presentation, COPT turns out can solve a wide range of problems, LPs, MIPS, MIS-OCPs, nonlinear problems as well, MIQCPs, QCPs, non-convex, convex, and so on, right? So what did you actually do today? We solved very large linear problems with PLP and the GPU modes. And we saw that for a large problem, actually it runs in 10 seconds when compared to 200 seconds on dual simplex. We also solved a non-convex quadratic problem when we need a certificate, when local solvers get stuck in local invisibility points. We now have a special branch and bound that will prove the global optimal on ACOPF problems, where when the local search will basically return nothing. And we also solved non-convex conic problems with integers, sorry, barrier for the QP1s and the SOCCPs, and branch and code when the integer variables start coming across all three portfolio stages. And the one that ties it all together, we solved with one solver, with one license, everything in the last hour ran in a single COPT installation with driven to and from AMPL, LP, non-convex QCQPs, convex QPs, SOCPs, and MISOCPs. There was no per class licensing, there was no second vendor. Everything ran with AMPL and sealed. Try it yourself. How to actually do this? How do you actually get to try this? We will be sending the notebook to the webinar participants as soon as this ends. This will run free on an Ample Community Edition plus a SEO trial. So be sure to link to visit portal.ample.com and set up a SEO trial. The notebook and these slides will go out to everyone registered after the session. Where to read more? For reading, dev.ample.com has the full COPT options reference, every option in the slide panel that we were moving, and several hundred more. Ample.com for the licensing, for commercial and academic licensing, and also the notebook repo for today's code. So you can scale it and run on your own hardware, which I will encourage because your crossover point for your problems will not be the same as mine, as you find your specific applications for whatever it is that you're doing. That's it for the hour. Tiancheng and I are both here. I don't know if you have any questions. Feel free to write those down in the Q&A section, please. And yeah, I guess that's it. Thank you very much for attending and listening to us. I don't know if you want to say anything, Tiancheng, for the before we start the Q&A session.
Oh, and all good on my side.
Great. So let's wait for some of these questions to start rolling. Actually, we did less than an hour, 50 minutes, so that's nice. So we can keep respect everyone's times. If no questions show up, Q&A. Okay. I have some questions on my own, actually. Um, so we'll wait if we have any questions specifically. Mm, mm, mm. So I have a question, for example. I know that COP 8.0 is the latest version. Um, I will say, or well, it's a question that I more or less know the answer to, but it will be reassuring to hear it from you. But I do not necessarily need a GPU to benefit from COP 8.0, right, Tiancheng?
Yeah, the PDLP was introduced in 7.2, but the barrier, I would suggest you run it with 8 with the most up-to-date version because we had some bug fix from now and then. I would suggest the new version. And same
Okay.
for the PDLP as well. I think that the performance-wise, I would always suggest the new
Yeah.
version.
And actually, we have a question from Professor Anthony Papavassiliou in the audience, a very similar one. Thanks for the presentation. Can you give me some more details on the GPU implementation of the interior point barrier algorithm? It sounds great, but in practice, the factorization is not obviously parallelizable. If it is, are there circumstances where it is preferable to use PDLP over interior point on GPU?
From my side, I would say e-alliance with the demos today. I think for large scale or super large scale problems, and it maybe I think that's where PDLP will show some advantage. you can refer to the CUPDLP paper where we uh, goes into detail of one single instance. It's called the zip 03. It has maybe millions or tens of millions of variables and even hundreds of millions of non-zero uh, elements in the coefficient matrix. So that's uh, a huge challenge for CPU-based algorithm. Uh, and for barrier, I would say if if the CPU barrier performs uh, better than the CPU dual simplex, maybe on GPU is naturally faster. Yeah.
And we have a follow-up question. So GPU interior point has a clear limit on scale, right? This is what Professor Anthony asks again.
Mm, I would say yes. For the GPU barrier solver in COPT, we currently there's a parameter called GPU mode, and the default setting is GPU mode 1, which just run something on CPU, run something on GPU. But if you set GPU mode to 2, the whole the implementation will be more aggressive, use GPU more aggressively, but it also comes with more consumption on memory. So in short, in one sentence, it's faster but consuming more memory. And in terms of a clear limit, I think also it also depends on the type of GPU, the size of the RAM of the GPU. Yeah.
Yeah, yeah. I just want to add just a little bit to this. Yeah, traditional sparse solvers use pivots, numerical pivoting, which is hard to run in parallel on GPUs. And then you have your matrices, which also become ill-conditioned as you reach an optimal solution. So what happens for GPUs is that you typically transform the KKT matrix into a symmetric positive definite matrix. So now this will allow you for fast Cholesky factorizations without pivoting. And now you start using iterative solvers like conjugate gradient instead of direct factorization. And this will allow you to run this faster on GPUs. There are tons of papers out there for both the barrier and the PDLP, which is the most known algorithm for running on GPUs. But I think that this is quite fascinating. On the barrier method has been around for decades, and GPUs as well. And it's now the very reason that we have been integrating, well, solvers have been integrating these two technologies at once, which allow us to push the boundary and solve larger and larger LPs. Hopefully, one day we can get something for MIPS. Seems unlikely, but we'll wait for that. Um, I don't know if we have any more questions from the audience. Not, I have more prepared. Um, mm, mm. So, for example, I have another question regarding the local mode on the ACOPF. Um, do you have any specific mm, guesses or insights as to why the nonlinear model failed to reach any solution at all? Tiancheng?
I don't have a quick answer. I think I may have to look into the logs, yeah,
Yeah,
of the solver. Yeah, I
yeah,
think
but
for different nonlinear or different non-convex structure, it has different difficulties
yeah,
for any local solver. Yeah.
yeah, yeah, makes total sense. There are other local solvers, nonlinear local solvers out there that will also fail with the same problem. But the good
Mm-hmm.
thing is that actually we have the global guarantee, which is through the spatial branch and bound.
Mm-hmm.
Yeah,
Mm-hmm.
which is a very nice strong point on COP side. Because there aren't many nonlinear solvers out there, as you may know. We have, uh, for example, for the open source world, you have IPOP. For example, IPOP doesn't work once you introduce
Yep.
integer variables, and you have your commercial ones. And your commercial ones are either local solvers or global solvers, but the global guarantee comes at a cost in time as well. So there's
Mhm.
no silver bullet for nonlinear problems. Um, I see we don't have more questions from our audience, so we'll wait for just a couple of minutes to complete the hour, and if not, then it was a pleasure on my end, Tiancheng, to host you, to work with you through the COPT internals and the benchmarks and so on. So I'm very glad to have the opportunity to collaborate with Cardinal Operations closer.
Likewise, thank you so much for inviting us.
Yeah, no, it's always a pleasure to work with our solar partners and to expand on them and see the harder problems being solved every single time. And best of luck with your future releases. And
Mhm.
hopefully, we see each other at Informs or iForce or whatever comes up
Okay,
along.
definitely, definitely.
Definitely, definitely. Well, no further questions. I want to thank everyone for. Okay, actually, how one more question. Okay, thank you, Joshua, as well. Joshua Bentley is
Thank you.
thanking us both, so thank you very much. If not, then that's it for today. That's it for the AMPL and the C of the webinar. Thank you very much for attending. Thank you very much for your time and attention. If you have any questions, please be sure to reach out to either me or Tiancheng or the larger AMPL and COP teams. We'll be sending the material for all of the attendees registered, and hopefully we can see you next time on our webinar series. Have a nice day, afternoon, evening, depending on where you are, and see you soon and take care, everyone. Thank you very much for attending.
You.
See you. Bye bye, everyone.